Okay, so this is going to be Chem 151 final review. So I'm just going to go through the entire review packet that you have. I would suggest you stop and you just take this with, your calculator, the crib sheet that you're given, and just give it your best attempt. And then look at what you're missing, look at what you struggled with, correct your grade your test and find out where you're struggling, and then take a look at this. So I'm going to go through this and I'm going to kind of annotate and kind of talk through my thinking on every single one of these problems. Maybe throw some equations out there, throw some stuff out there. I'll probably break it up. So this is 80 questions. That's quite a bit. I'll probably break this up into 3 videos. So 80 questions, maybe 4 videos. So I'll do probably 20 questions and then break it up. So this is 1 through 20. Here's 1 through 20. All right. So which statement is correct about ideal gases? Okay, so we have to recognize that the gases, what makes a gas is, first of all, it's compressible. So that means that pressure and temperature and volume are important. But most importantly, when we talk about gases, we treat it differently than solids and liquids because there are no intermolecular forces. Because there are no intermolecular forces, this puts us in a position where we have to think about them differently. Every single gas is going to behave the same way, regardless of the type, and that's because there are no intermolecular forces that we ever consider. So the ideal gas means no intermolecular forces. So atoms or molecules in gaseous state don't attract each other, don't repel each other, they don't interact. So that's when something is behaving in an ideal circumstance. There are 2 equations that we need. PV equals nRT. I'm just kind of setting this up in case we end up with another gas one. I'm sure we will. P1 V1 over N1 T1 equals P2 V2 over N2 T2. And I can get from PV equals nRT to this combined gas law by just solving for R. If you solve for R, you're going to end up with just this. And if we have 2 states, they are both equal to R. So with this in mind, we can kind of work our way through all of these in terms of just thinking about conditions where we're changing pressure, changing temperature, and those types of things. But let's take a look at the question. So which of the following is a correct statement? Okay, so let's take a look. At constant temperature, okay, so temperature doesn't change, pressure is directly proportional to the volume given. So let's consider that. Pressure versus volume. So if we take some large container and we reduce, so this is got X number, let's say 5 little molecules in it. This is volume 1, and we reduce its size. We reduce the volume, so volume 2. So as volume goes down, what happens to the pressure inside? So more molecules, same number of molecules. So as volume decreases, so if it is directly proportional, which this thing is asking us about, that means that they're going to go in the same direction. So as volume decreases, what we expect to happen. So imagine this, right? So imagine what happens if you take this and you compress it, okay? What we expect to see is we actually expect to see an increase in pressure. So they're actually inversely proportional. And you don't need to know the equations in order to do this. Just consider a balloon or consider something in the real world and to decide what's going to happen. So decrease in volume equals a decrease in pressure. Okay, A cannot happen. Okay, it's not true. All right, next up. At a constant pressure and temperature, the volume is inversely proportional with the number of moles of gas. Okay, so we can actually use the first one that we just had. And let's now consider that pressure is going to remain constant, but let's see here. Pressure and temperature are constant. Volume is inversely proportional with the number of moles of gas. So if I have this large container, but we can change the number of moles of gas, well, pressure has to remain constant. So if we start in that first condition where I have 5 gas molecules and I compress it, we know the pressure goes up. So we actually have to lose some of the gas molecules in order for volume to change. So as volume decreases, that equals a decrease in the number of moles. We have to decrease the number of moles because more molecules means more pressure, but keeping it at a constant pressure, we need to essentially get rid of some of that stuff. So that means that these are, in fact, directly proportional. Volume and moles are directly proportional, but it's saying that they are inversely proportional. Nope, that's wrong. So we can eliminate that as well. All right, at standard temperature pressure, 1 mole of gas occupies 22.4 liters of space. So this is true. So this is going to be our answer. But what we really should look at is how do we actually get this number? If you're not provided this number, you have to recognize that, okay, standard temperature pressure means we're dealing with standard temperature, 0 degrees Celsius, standard pressure, 1 atmosphere. You can always solve for this value by just simply plugging it into PV equals nRT. Okay, 1 mole of gas. Yeah, so we would know that 1 mole of gas. So I'm going to solve for volume. Volume is equal to moles. 1 mole of gas are, I'm not going to plug it in, but temperature of 0 degrees Celsius, which is 273 K, and a pressure of 1 atmosphere. If you solve this, what you're going to find out that volume is actually equal to 22.4 liters. So yeah, that is true. You can always use PV equals nRT. In fact, I usually tell my students to use that to determine the fourth state or the third one. All right. And finally, deviations from ideal gas behavior. Let's make sure that we're answering correctly here. Deviations from ideal gas behavior are observed at low pressure and high temperature. So again, ideal gas behavior means no intermolecular forces. That's what makes it an ideal gas. So do we expect to see that at low pressures and high temperatures? Well, high temperatures are actually not conducive to intermolecular forces. They're moving too quickly to actually interact. Low pressure means that essentially there aren't a whole lot of interactions happening. So it's actually the reverse of this. At a high pressure and a low temperature, that's generally when we see deviations from the ideal gas behavior. So this is in the opposite direction. We'll eliminate that. Okay, so gases, that's it. We're probably going to come up with a couple more. Come back to this question if you ever have. I'll probably refer back to this question for other gas problems. All right, moving on. So which of the following is not an intensive property? So we've got a term here, intensive property. That means it is independent, intensive, independent of amount. So regardless of how much you have, we're always going to have the same, we're always going to have, it's going to be independent of the amount, as in the density is always going to be the same. The density is always going to be the same. The volume is always going to be the same. So it's always going to melt at the same temperature. So basically a physical property that is independent of the amount, but it tells you, essentially it describes the substance. So if you can identify something based on that property, that's probably an independent or an intensive property. So it is solid at 25 degrees Celsius. So is that intensive or extensive? No, I mean, knowing that something is solid at 25 degrees Celsius, that should be true whether we have 1 gallon of it or 10 gallons, or should be true if we have 1 gram or 1,000 grams. So yes, this is intensive. So we're looking for not an intensive property. So this is absolutely intensive. B, it has a density. Density, we use things to identify density all the time. So we're going to call that intensive as well. All right, what's next? Melts at 60, any boiling point, freezing point, anything like that, also going to be intensive. It's independent of amount. Everything, regardless of how much we have, it'll always melt the same, always have the same density. So that means volume. Volume does change. If I have 1 gallon or 10 gallons, that's different, right? So volume is going to be our answer here. It is and it's an extensive property. It does depend on the amount present. All right. calculate the following with the correct number of significant figures. All right, let's pull out our calculator. Again, actually, we don't really need to pull out our calculator, but we kind of do to see if it's D. I'm guessing it's not going to be D, just because all of the other answers, this is a sig figs question, right? So we have to follow PEMDAS. And so we always follow PEMDAS. I always want to do the parentheses first. I can do both parentheses at the same time here because they're going to kind of be independent of one another. So I'm going to rewrite everything else, 0.288 plus, and then whatever that is. So first I'm going to do is 1.428 minus 1.08. I probably could have done that. Actually, so 0.348. Okay, that's what I got out of my calculator. But what I really want to do is I want to take a look at this problem and I want to decide where I would round. Okay, so the number for this is 0.348. That's the result of this. Okay, because we are subtracting, I'm interested in the number of decimal places. This has 2 decimals. This has 3 decimals. We're going to reduce it to, we're going to always round to the least number of decimals. So that means I'm going to underline the 4 here because I would round to the second decimal place. We're not going to round until the very end. So that means I'm going to underline the 4 in my math there. Next up, I'm going to do 2.83 times 0.360. That gives me, write the number here, 1.0188. I'm going to give everything the calculator gives me, 1.0188. And because we're multiplying, I'm interested in the least number of sig figs. This one has 3 sig figs. This one has 3 sig figs as well. And so that means simply I'm just going to underline the 3rd sig fig. I'm going to round to the 3rd sig fig. There we go. All right. Now let's take a look at our new problem. So again, we are keeping track of where we're going to round, and but we're going to keep those entire numbers. So what's the next thing you want to do? PEMDAS, we did parentheses. We have no exponents or roots. So we're going to do multiply and divide next. So I'm going to do the 0.348 again using the entire thing, divided by 0.288, and that gives me 1 point. So I'm creating a new problem, 208, and this is 3 repeating. Just put a couple 3s there, fine, plus 1.0188. I'm going to underline, I'm going to keep that 1 underlined. So now we're going to, when we divide like we did here, I am interested in the number of sig figs. This one has 3 sig figs as written, but because I have this underlined one here, it would only have 2 sig figs. So I'm going to say that that would have 2 sig figs. This would have 3 sig figs. So I'm going to underline the 2nd sig fig in my new answer. Okay. And now I'm going to add these 2 together. So 1.2, again, taking the entire thing, 0.0188. This gives me a value of 2.22713. And again, because we are adding, I'm interested in the number of decimal places. This has 1 decimal or space. So if it was rounded to the 1's place, it would be the 1's place, it would be 0 decimals or the 10's place, but generally don't run into that. This has 2 decimals. That means that I'm going to underline this first decimal because that's the one that wins. That's the one that won there. And so I'm going to round this to that place, which is underlined. So 2.2, that should be our answer. So it should be C. 3 should be C. Yep, 3 should be C. There we go. So this was D, this was C, and this one was C as well. All right, moving on. So next up, let's see here. Consider the process occurring in a pure CCl4, so carbon tetrachloride, at its boiling point. Okay, so it's boiling point. What's going on at its boiling point? CCl4 is going on at its boiling point. Which equation best represents this process? Okay, so it's boiling. that indicates that this is a physical change, right? This is a physical change. So any chemical changes we can eliminate. Boiling point indicates it's just boiling. So C is going from a liquid to its components. You can just eliminate that. It's not going through a chemical reaction. This is just a boiling point. It's going through a physical change. This is the opposite. We're not even starting with what we're looking at. So it comes down to these two. And really, am I going from a liquid to a gas or a gas to a liquid? We are going from a liquid to a gas. That's the point of boiling, right? Boiling is going from liquid to gas. So 4 is going to be A. All right, moving on. How many protons, neutrons, and electrons? Okay, so now we have a couple, 2 problems the same. So I'm going to pull out my periodic table so I can solve this. We got to find this. All right, so here we go. 247 cm. That's all the information that I'm given. What we'll notice is a couple of things. So zooming in on this, what do I know? That's where my charge goes. Charge is always going to be essentially the difference between protons and electrons. It's the number of protons minus the number of electrons. Overall, that's going to give you the charge. Okay, so if I have extra positive charges versus extra negative charges, you're always going to kind of weigh it out. We don't have one here, so we know in this case that protons and electrons are going to be the same. So I can actually go through and look for every single one of these, protons and electrons, 247. So A has 247 and 247. That can be a possible answer. I can eliminate, oh, sorry, not 247. We'll get there in a second. Sorry about that. Cm. So I've got to find Cm on the periodic table. 247, yeah. Curium, which is down in the actinide series, is going to have 96 in this. And that's the atomic number. So that's the atomic number. This is the number of protons. So we know that protons is 96. That means I can immediately eliminate A and B. And actually, we're pretty much done here. We don't really have to do more math because we know there's no charge. It's neutral. That means that protons has got to equal electrons, and D is the only one where that actually happens. So this would be D. We could eliminate C. The last portion of this is just simply taking 247 minus 96 should give me 151, because this value up here, as we know, is protons plus neutrons for the total mass. So that's going to give us the full mass. 247 is the mass because that's all the stuff that's in the nucleus. But we actually don't have to get that far because we know it's neutral. And so those two have to be equal. All right, next up, copper 2 plus 64. So copper 64. So let's take a look at this one. So copper 2 plus 64. And so I'm going to look at my periodic table. You can always link the element with the atomic number, 29. So I know that it has 29 positive charges. So taking a look at this, I see that it has a 2 plus charge. I always tell my students to remember this. I'm positive I lost an electron. That's going to help you remember that if it's positive, that means that you're losing electrons. So if I start with 29 protons and 29 electrons, this whole thing is going to be neutral. But I want it to be 2 plus. That means I actually have to lose 2 electrons. So I'm going to have 29 positive charges and 27 negative charges, electrons, after I lost the 2. That's where that came from. And the net result of that is positive 2, giving us our positive 2 value here. Okay, so I'm positive I lost an electron. I start with a neutral amount of electrons. I lose 2. I have 27 electrons. Let's see if that's enough. So first of all, 29 protons. Eliminate this, eliminate this. And we have 27 electrons. Both A and C have 27 electrons. Okay, so can't eliminate one of those. So the last little bit here is we're just simply going to do, so 64 minus 29. Subtract those two, and I'm going to get 35. 35. So I should have 35 neutrons. C, eliminate A. So the answer to this should be C. Okay, that's pretty much it. All right, let's take a look at the next one. Which of the following is most likely to form? Okay, so if we look at the periodic table, we know the number of valence electrons based on where they are in the periodic table. So group 1, sodium, potassium, lithium, all the stuff in group 1 is going to have 1 valence electron. And all the way at the other end, group 18 or group 8 is going to have 8 valence electrons. We ignore essentially the 10 and we just look at the group number. Group 1, 1 electron, group 18, 8 electrons. And then we have to make a decision. If we're looking at something in group 1, my question is it easier to lose 1? Because remember, we want to go to 0 electrons, which takes us back to the previous noble gas, or gain 7, which is going to, or sorry, gain up to 8 to get us to the next noble gas. So easier to lose 1 for group 1, easier to lose 1 or gain 7. It's easier to lose 1. And the charge of that becomes +1. I'm positive I lost an electron. How about group 2? Well, group 2 has 2 valence electrons. Is it easier to lose 2 or to gain 6? It's easier to lose 2 electrons. Group 2 is going to be +2. Let's go all the way to the other side. Group 17, which is actually 7 electrons. Easier to lose 7 or gain 1? We're going to gain 1. Okay, so if we look through this, we find out that aluminum, I need some space here. We know that aluminum is in group 13 or group 3. So we expect aluminum should be aluminum, well, easier to, we got 3 valence electrons, easier to lose 3 or gain 5. It's actually easier to lose 3. So we expect it to be 3+. Magnesium, this is in group 2. Easier to lose 2 or gain 6. Magnesium should be 2+. Looks like this is the right answer. Next up, sodium. Sodium is in group 1. Okay, so if this is in group 1, it's got 1 valence electron, easier to lose 1. We actually expect sodium to be +1. That's not it. And then fluorine, this is in group 17. We expect fluorine to lose 7 or gain 1. We expect it to lose or to gain 1, giving us a -1 charge. So we expect magnesium to be the correct answer here. All right, next up. The melting point of pure benzoic acid is 122 degrees Celsius. Data obtained from the 4 students in a laboratory are shown. Which students' data are precise but not accurate? Okay, so we have to define these two things. Precision versus accuracy. So precise, this is just knowing definitions. Precise means that all of your data is clumped together. So data is close together. Every single trial you do is really close together. Like, so of all of these, which of the following are precise? So student C, that's pretty precise. This is student D. Well, actually, I'm just going to do this. Precise versus accurate. So we'll deal with precise first. Student A, we see a pretty big delta between those, right? A pretty big change. So I would say that that's not really precise. Student B is actually pretty precise because all the numbers are within 2 degrees of each other. Student C, very precise. They're all within 1 degree of each other. Student D, not precise. Okay. And then finally, accuracy, or secondly, accuracy. The data average is close to the accepted value. So it doesn't matter how precise you are. If your values average out to be the right to be pretty close, then we're in good shape. So we actually have to take a look at the accuracy, and the accuracy is going to depend on 122 degrees Celsius. So student B, student A, it doesn't look like, if I averaged these together in student A column, that would not be anywhere close to 122. Student B, actually those numbers look pretty, certainly closer to than the first student. Student C, these are definitely, student C is definitely accurate. I guess we probably would say that student B is probably not accurate because it's not as close as student C is to actually having the average value. Student D is not precise, but it looks like they are going to be accurate. So which student is precise? So I think I have every combination here, and not accurate. So it looks like student B. Student B, the average value is close to, is not close to 122, although it's, 119 it looks like, but it is very precise because all the values are pretty close to one another. So in this case, student B, precision, all the data is clumped close together. And then accurate means that whatever your average is close to what the true value is, which we know is to be 122. All right, moving on. Boron has two naturally occurring isotopes, B10, B11, and with those, so calculate the percent abundance for each isotope. Okay, if we know that the average mass for this. So if we're doing this calculation, we're always going to essentially take an isotope times its mass abundance fraction times. So here we go. So first of all, let me just make sure all of these add up to 100. They do. So together, B10 has a mass of 10.013 AMU times its abundance. So we'll just, times its abundance. Yeah, more, what do I use for that? We'll just use the boron abundance. Plus the 11.009 AMU times its abundance. So now we've got actually two, we'll call that abundance X. Oh, that's going to get confusing. We'll call it A for abundance. All of these, we can't really call this abundance either. So those two things together have to be 10.81 AMU. Okay. So this is a little bit more finicky. So we know together, both of these, we'll do it up here. We know together, both of those have got to equal 100%. So if I know the abundance of one, so if I know the abundance of B10, we know that the abundance of B11 is going to essentially be 100 minus whatever A was, right? So we have to have those two abundances together. They're going to equal 100%. So if I know A is 90%, we know that so if I know the abundance of B10 is 90%, I know that B11 has to be 10%. So essentially 100 minus whatever A happens to be. So this is what it comes down to here. We're just going to essentially do this math. Not particularly enjoyable to do, but this is how you're going to solve this. I'm not going to walk through how to solve this. This should be pretty straightforward. You're going to have to distribute the 100, and then solve for A essentially, and then plug it back into the equation. But it looks like the answer for this is going to be C. So you should end up with C for this answer. I'll let you do the math. I believe in your math skills, but that's how you solve it. Essentially, the abundance of 100 minus the abundance of the other to give you the total abundance. And we know that abundance is always, the percent abundance is always based on atomic number. By the way, I should also mention that your abundance value is going to be a fraction. So you're going to have to multiply that by 100. So anyway, all right, moving on. Which of the following is not classified as a molecular compound? Okay, so molecular. They come in two forms, especially just for this class, really. Molecular means no no metals, really. Or more accurately, really what a molecular compound, it is not ionic. So it's not ionic. So CO, that right there is going to be carbon monoxide is molecular. It's a molecule. It's not an ion. C2H4, anytime you have carbon and hydrogen, carbon and a bunch of hydrogen, generally it's going to be molecular. C6H12O6, yep, molecular. Anytime you have carbon, a bunch of hydrogen, generally molecular. Okay. This, however, I have C2H3. So I said when you have a bunch of carbon, but you have to recognize this right here is an ion, NH4 plus. This is ionic. So we're looking for ionic compounds. So we're looking for metals. We're also looking for polyatomics, NH4, also the other one, C2H3O2, that's acetate. So we're looking for, it's a little bit tricky because it's not fairly obvious. Also, the other thing that I would be looking for is acids. So HCl, HNO3, right? So any of those would also kind of, so acids, for ionic acids, we have a metal or we have a polyatomic. Those are the things that we're looking for. So in this case, D is the correct answer. Moving on. What is the correct name for an aqueous solution with the formula HBrO3? Okay, so H, this is helpful. H indicates that it is in fact an acid. So all of these are acids and all of our names are in fact acids. Okay, so HBrO3, I do have the naming scheme. So for HBr, we're going to use that one. It's always going to be hydro. We're going to use the root ic acid. So hydrobromic acid. The hydro part is essentially saying you have just two. It's a binary acid, H and the Br. So anything that has hydro in the beginning, we can immediately eliminate. Okay. Next up, hydrogen. So if we look at the next thing is the BrO3. So we have to know, is this bromate or bromite? And so that's really what it's going to come down to, whether you know bromate or bromite. So BrO3, think about other things that you know, Cl, that are in the same category, ClO3, ClO4. So what we really want to know is essentially, is this ate or ite? And so what this comes down to is any polyatomic with an AT ending is going to turn into IC acid. So I'm going to change that to IC acid. Anything with a ITE ending turns into OUS acid. So I need to know what BrO3 minus is. So BrO3 minus is going to give us it. So bromite, okay, ite goes to us. And the way that I remember this is dumb, but ate, ick, ite, us. Sounds like a disease. Aidic itis. Ate goes to ick. Ite goes to us. So BrO3, we have to decide. Turns out that is bromite. So bromous acid, your answer for 11 should be D. All right. What is the correct formula for copper 2 nitrate? Okay, we can do this quick and easy. Copper 2, anytime you have a Roman numeral, just be happy because it essentially just tells you the charge. Every time it tells you the charge. Nitrate, NO3 minus, I know that's polyatomic. So if we do, you can take the number and give it to the other one. So I'm going to need 2 nitrates. That 1 for nitrate is going to give me 1 copper. So 1 copper and 2 nitrates. I'm going to always put it in parentheses if I have more than one. There we go. So get rid of C and D. And we actually have 2 nitrates. So the answer for this should be B. All right, moving on. Which of the following name pairs is correct? Okay, let's take a look. So iron oxide. Okay, that's good. Well, I guess we can start with the first one. Phosphorus oxide. Great. So do I need the pent in front? I do. Anytime you have 2 nonmetals, there's no oxidation state, so there's no charges that we can really, so we have to tell the reader. So I do need prefixes for this one. So I have 2 phosphoruses, so that should be diphosphorus. Pent is correct. That means 5. So we can eliminate this one because it's correct except for not having diphosphorus. Next up, iron oxide. Okay, good. Iron oxide. This 2 indicates that this is Fe2 plus. Is it Fe2 plus? Well, let's take a look. Iron, we know oxygen is -2. We know the whole thing is neutral. So we expect all of the oxygen to be -6. So what has to go in here? I need a +6 total for all of the iron, but I have 2 irons. That means that each individual iron is +3. They have to split that +6 charge in order to make it. So, and also the 3 down there. So this should be iron 3 oxide. So this is incorrect as well. Moving on. Dihydrogen monoxide. Okay, so again, hydrogen oxide, that's correct. Because I do not have a metal out front, that means I need to use prefixes. So di means 2, good. Mono means 1, good. So it looks like B is correct. Let's check the last one. Potassium oxide, because I've got potassium and oxygen. I do not need prefixes because I have a metal. So I can eliminate that. The correct answer for this one is going to be B. Which sample represents the greatest number of moles? Okay, so we have to convert these things to moles. All right, let's take a look. So grams to moles, I just need to do a conversion with the molar mass. So 44.01 grams of CO2 times fraction 1 mole on the top, grams on the bottom. What is the molar mass of CO2? Well, it turns out carbon is 12. I'm just going to round here. And oxygen is 16, but I have 2 of them. So 32 plus 12 gives me 44 grams. So yeah, this is 1 mole. So 1 mole. This is also 1 mole. So this is correct. This is also correct. And 6.02 times 10 to the 23rd, also 1 mole. Okay, so in every single instance, D is the correct answer here. They're all equivalent to 1 mole. Next up, calculate the number of carbon atoms in 25 grams of isopropyl alcohol. Okay, so again, we're going to do a conversion, 25 grams. And because we're so we're looking for the number of carbon atoms. So this is going to be conversion. Maybe I'll do it down here, actually. Well, I think I did it. 25 grams of isopropyl alcohol. That means I'm going to need the molar mass. So 3 times 12, there's my carbon, plus 8 times 1, there's my hydrogen, and plus the 1 times 16, there's my oxygen. So let's get the total for all of this. Let's see here. Okay, there we go. So 12, so that's what, 36 plus 8 plus 16 gives me a total of 60 grams per mole for isopropyl alcohol. So grams in the bottom, moles on the top. 1 mole is equivalent to 60 grams. So right away, I'm going to figure out moles of, and maybe it's probably important to do this, moles of C3H8O, right? What we're really looking for is the moles of carbon. Are we looking for the calculate the number of carbon atoms? Number of carbon atoms. So within one of these, so 1 mole, or I should say a mole of, I'm going to slide this out of the way a little bit. I need a little more space. I'm going to do this below. Okay, so this belongs to 15. So what I really want to do is the number of carbon atoms here. So let's focus in on this. So I actually don't want moles of C3H8O. I want actually moles of carbon atoms. For every 1 mole of C3H8, I have 3 moles of carbon. And that's true for all of these. I have 3 moles of carbon. I have 8 moles of oxygen. I have 1 mole of, 1 mole of oxygen, 8 moles of hydrogen, right? So moles of C3H8 cancels, and I'm going to be left with moles of carbon, but it's actually asking for how many moles of total number if we want to count. So 1 mole of carbon atoms is equal to 6.02 times 10 to the 23rd carbon atoms. So moles of carbon atoms cancel, and we do math. So we can eliminate those numbers because we know it's going to be a massive number. And we can actually, and we don't quite know. So looking at this, doing the math, we end up with what looks like, let's see, 15 D. So D looks to be the correct answer. You should get that when you plug in all of that. I don't need to walk through the math. 25 divided by 60, enter, times 3, enter, times 6.02 times 10 to the 23rd. All right, next up, what is the empirical formula that is 43.7% phosphorus and 56.3% oxygen by mass? Okay, so first thing we're going to do, we're going to assume 100 grams, because what that does, that means a percentage turns into a gram quantity. So what that really means is I have 43.7 grams of phosphorus and I have 56.3 grams of oxygen. But when we're looking at a formula, an empirical formula, what I know is Px, O, Y, those X and Y values are moles. So the first step I have to take is I want grams of phosphorus to go away and I want moles of phosphorus to remain. So 1 mole of phosphorus is equivalent to the number 30.974.974. So what is it? 43.7 divided by 30.974 gives me 1.41 moles of phosphorus, which means my phosphorus is 1.41. Now my oxygen. Oxygen is 15.99 grams of oxygen per 1 mole of oxygen. So 56.3 divided by 16. 50, let me try one more time. 56.3 divided by 16 gives me 3.52 moles oxygen. So my oxygen value is 3.52. I always want to divide, we want whole numbers here, so I'm going to divide by the smallest number I have, 1.41, divide by 1.41. So that means that this turns into 1, and 3.52 divided by 1.41 gives me 2.49 or 2.5. Okay, so we still don't have a whole number, which is annoying, but we have a simple solution for this. So I'm just going to take that number and I'm going to rewrite it. So I know that I have 1 phosphorus and my oxygen of 2.5. What can I multiply this by in order to get rid of that fraction, or each of those numbers by? If I multiply this by 2, right? So that means I now have 2 phosphorus. My oxygen, 2.5, becomes 5. And so there we go. P2O5 should be our answer. P2O5 is our answer. The answer for this is C. All right, it's been a long one, but here we go. 4 more questions. or three more questions, I suppose. The overall equation involved in photosynthesis is this. Okay, so 6 CO2. Okay, great. How many grams of glucose form when? Okay, so this is a stoichiometry problem. We should, whenever we're given an equation, it's asking for grams of glucose and it's giving me some other chemical. So when I switch from one chemical to another, so I've got CO2 and I am converting 2 grams of glucose. So I'm going from one chemical to another in a balanced chemical equation. This is stoichiometry, period. Okay, so this is going to be stoichiometry. So let's set it up. So I start with the original number, 4.40 grams of CO2. I'm always going to label what I have. And the first thing is I need, if I want to switch from one chemical to another in a balanced chemical equation, I need to go to moles first. So times fraction grams of CO2 to go away, moles of CO2 to remain. 1 mole of CO2 is equal to 44.01. I think it's 44.01 or 44.1, but this is multiple choice, so we're just going to do 44. At this point, grams of CO2 is going to cancel. Next step, and the only time I use the balanced chemical equation. So I want moles of CO2 to go away, and I want to end up with moles of glucose. So C6H12O6. If I look at my balanced chemical equation, 6 moles of CO2, 1 mole of glucose, moles of CO2 cancels, and I have moles of C6H12O6. So we're in the home stretch here. The last thing I've got to set up is I want moles of C6H12O6 to go away, and I want grams of C6H12 to remain. So 1 mole is equivalent to, and let's see what molar mass. So this is going to be 12. Oxygen is a 6 times 16. Round it for the most part. Doing, oh, that's way too many. Let's see, 6 times 16 gives me 96. And then 6 times 12 gives me 72. So 72 plus 12 plus 96, 180. So 180. And now we do the math. So 4.40 divided by 44, enter. Divided by 6, enter. Times 180, enter. Oh, can't see my number. All right, one more time. 4.4 divided by 44, enter. Divided by 6, enter. Times 180, enter. Gives me 3. So about 3 grams, B. There we go. Done. All right, next up. The rapid decomposition of sodium azide to its elements for this reaction. Okay, again, another one. Grams of N2 from grams of sodium azide. Okay, this is another molar mass, or this is, we're switching chemicals. I'm going from one to the other. So again, this is a stoichiometry problem. I'm not going to walk through this one because you should have this one the same way. Looks like the answer for this one is going to be A. Okay, so should be the same setup as above, only using the stuff that we have here. We're going from, what is it? Sodium azide to N2. So that's the transition you're going through. You know, grams to moles to moles, and then moles back to grams. All right, 19. Then we're going to get through 20 because I said I would do 1 through 20 here. Excess water reacts with 25 grams. Okay, so excess water reacts. Okay, 25 grams of, there's 1 to produce lithium hydroxide. If the yield is 22.3 grams, what is the percent yield? So this is actually, are we switching chemicals? Yeah, we're going from lithium to lithium hydroxide. Lithium oxide to lithium hydroxide. So we are switching chemicals. So this is both a stoichiometry problem as well as a percent yield problem. So this is the experimental yield. We want to figure out what the theoretical yield. We don't have to worry about a limiting reagent because we were told that water is an excess. So with that in mind, we start with our original number of 25.0 grams of lithium oxide times fraction. I want grams of lithium oxide to go away, and I want moles to remain. And this is why it's annoying, because now I have to do math. Let's see here. Lithium, so 6.94 6.94 for the lithium times 2 plus 16 gives me 29.88. So 29.88, this is the molar mass of lithium lithium oxide. All right. So next we need to go from moles of lithium oxide to moles of lithium hydroxide. And according to the balanced chemical equation, 1 mole of lithium oxide is equivalent to 2 moles of lithium hydroxide. A little more space here. So, okay. There's not a whole lot of space to do these problems, are there? And then finally, I'm going to convert back into mass. So I want moles of lithium hydroxide on the bottom. I want grams of lithium hydroxide on the top. 1 mole of lithium hydroxide is equivalent to, so lithium is 6.94 plus the 16 for the oxygen plus the 1 for the hydrogen gives me about 23.94 grams. And so now we do the math. Let's do units first. Grams of lithium oxide cancels, moles of lithium oxide, moles of lithium hydroxide. So we should end up with grams of lithium hydroxide at the end. And so with that said, it is going to be 25 divided by 29.88 times 2 times 23.94 gives me about 40 grams of lithium hydroxide. So percent yield equation is going to be your experimental divided by your theoretical times 100. So in this case, it is going to be 22.3 grams divided by 40 grams times 100. So 22.3 divided by 40, just over, so 55.75%. So so this 19 should be B. Again, I rounded a bunch, so the number is not going to be quite perfect, but you get the point. All right, last one. What is the molarity? Okay, so molarity, need more space. I'm going to move this. What is the molarity of? So first thing we do, as soon as we see molarity, we've got to write out what molarity is. Molarity is equal to moles of solute over liters of solution. What is the molarity of a sucrose solution prepared by 125 grams of sucrose and 500 mils of solution? So first thing I want to do is figure out how many moles. So this is pretty easy. I have 0.5 liters, make sure that it's your solution, and 125 grams of my sucrose divided by the molar mass of 342.3. I have, which looks like 0.365 moles. So this is actually 0.365 moles of sucrose. So I'm gonna put that on top, 0.365 moles. So the number should be less than 1. So 0.365 divided by 0.5 gives me 0.73. So there we go, A. There we go. So molarity of 0.73. So again, that's the idea. Yeah, great. And that is that.